Hello there, Dr. Tishan here, and in this video let's take a look at integration by parts. This is a topic you would see in a Calculus 2 class. We're going to take a look at where it comes from. We'll do 3 examples, and then we're going to see a shortcut that I hope you're really going to enjoy the shortcut. Anyways, let's go ahead and get started. Integration by parts. This is a topic in Calculus 2. To see where it comes from, we have to visit a derivative formula that you remember from Calculus 1, the product rule from Calculus 1. Let's take a look at the product rule from Calculus 1 so we can see where integration by parts comes from. So the product rule, Calculus 1, when you're taking the product of function u times function v, right, what we do is we take the first function u, it gets multiplied by the derivative of function v, then you add to that function v gets multiplied by the derivative of function u. This is your product rule from your Calculus 1 class. Now what we want to do here is let's go ahead and just rearrange the terms. Let's take the v du, okay, we're going to take v du and we subtract this from both sides. Let's subtract v du from the left, we're going to subtract v du from the right, we're going to subtract v du from both sides of our equation, just to rearrange the terms here. So on the left hand side we have our derivative d dx, okay, derivative formula of u times v, the product rule, and we're subtracting v du because we moved this over. All right, on the right hand side you have the u times dv, and these terms right here are gone. All right, now let's just rearrange again. We're just going to rearrange. I'm going to take the left hand side, the right hand side, and just interchange them. Just interchange them so we can see where it's come from. So we're going to take the u dv, let's put that on the left hand side, and then let's put this difference on the right hand side, d dx of u times v minus v du. So we just interchange the left and right hand side. Now let's integrate both sides of the equation. We're going to integrate the left-hand side of the equation, the entire left. We're going to integrate the entire right-hand side. When you integrate the right-hand side, we can actually break the integration signs, and we can put it in front of each of the terms. So the left-hand side, we have the expression integral of u dv. That's what's on the left-hand side. The right-hand side, you're integrating a derivative. These operations are inverses of each other, opposites of each other, and so you're just undoing the derivative, so the integral of the derivative is going to cancel out, so you have your u times v left over. Then you're subtracting from that integral of v du, and what do we have here? This is your integration by parts formula. This is how you would use the integration by parts technique when needed, as you learned it in your Calculus 2 class. So, and again, it comes from your derivative, Calc 1 derivative formula for the product rule is where it's derived from. All right, so let's look at an example. Example number 1, we want to integrate x times the sine x dx. So as with integration, first thing you always have to do is you have to consider all integration techniques you've learned in Calculus 1. You have to consider that first. Can we use a u substitution? If u substitution works, you need to use u substitution to integrate this, okay? If we try to use substitution for this first example, it's not going to work. So we need another consideration for this integrand. And so if you look at the integrand itself, you have x, an algebraic function, being multiplied by the sine x, which is a trig function. Two functions being multiplied, so if u substitution doesn't work and your integrand is looking like a product of formulas, that is an indication that integration by parts needs to be considered as your technique, because the integration by parts comes from product rule. All right, so that's the technique we need to, we're going to consider using here. So how do we start? Okay, the first thing you have to do, you have to take this problem and we have to look at the integrand and we have to identify the u piece and the dv piece. We need to look at this integrand and we need to figure out which piece is going to be the u piece, and we need to figure out which piece is going to be the dv. We need a u piece and a dv piece. Now, how do we figure out which part of the integrand to let u equal, which part to let dv equal? We've got a little trick for that. And the trick is proven to be true. You can research it if you'd like to, but a little trick for that. There's a letter, just remember these letters in this order, okay? L, then I, then A, then T, then E. You need to remember this order left to right, L, I, A, T, E, right? These letters stand for the different types of transcendental algebraic functions. L stands for logarithm, okay, your logarithmic functions. I stands for inverse trig functions. A stands for algebraic, okay. T stands for trig, and E stands for exponential. So you want to remember your functions in this order, L, I, A, T, E. In my head, I say to myself, I late, but the I is after the L. That's how I remember it. I don't know, it might not make sense to you, but remember this order of these letters, okay? So we want to look here, okay, at this integrand. What do we have for our example 1? Well, x is an algebraic function, and the sine of x is a trig function. So we have algebraic, we have the algebra, we have trig. Those are the two functions in our example number 1. So as you go through these letters left to right, which one comes first? The algebraic comes first, which means u is going to be the algebraic function. So we're going to let u equal the algebraic function x. That's what u is, okay? So whichever function comes first in our LIATE, that's u, all right? So then what about dv? It's all the rest of it, okay? All the rest of it. So what do we have left over after we take the x out? We have sine x dx. It's all the rest of it, okay? All right, so first thing you want to do when you're going to use integration by parts, you need to take the integrand and figure out which piece is u, which piece is dv. Use our trick, all right? Proven to be true, you can research that. Next, we need to get the rest of the pieces, okay? So u, we need du. Okay, look what we need to fill in here. So let's find the rest of the pieces we need. We need du. Du, well, if u is x, du, the differential, we're going to take the derivative, okay? So du, all right, implies we want to find the derivative of x times dx. What is the derivative of x? It's 1 times dx. And so here's our differential here, all right? So we've got du, and then you see we need v. We need to know what v is. We know what dv is. How do you go from dv to v? You integrate to get from dv to v. So to get from dv to v, we're going to integrate. When you integrate the sine function, you're going to get negative cosine x. All right, so here are the pieces we need. All right, so once again, review. First step, identify u and dv. Identify your pieces. Use our little trick to identify the pieces, okay? Next thing you want to do is get the rest of the parts that you need so you can plug into the formula. So you're going to need to take u and get the differential du, and with dv, we're going to need to integrate to give v. All right, so now let's go ahead and put it all together. So our integral problem here, we want to integrate x times the sine x dx. Okay, so so what do we need to do to integrate x sine x dx? We want u times v. Look what we have here. We want to take u and multiply it by v, those functions there. U is x. Okay, so we want to take x and we want to multiply it by, I'll pull the negative out front, negative cosine x. Okay, so we have u times v minus the integral of v. V is our negative cosine x again, and then du, and du is just the differential dx. Okay, so here is so we integrate x sine x dx, u times v, so it's going to be u times v minus the integral of v du. All right, so we set it up. We're almost done here. We need to integrate, okay? We need to complete the integration. So let's just write this one more time. So x times the sine x dx is equal to, our first term is negative x cosine x, okay? And then minus and negative, so that's positive, all right? And then the integral of cosine x. When you integrate cosine x, you get sine x. All right, we're almost done. Okay, so this is an indefinite integral, so we need to remember to add our constant of integration at the end. Remember to do that when it's an indefinite integral. You need to add that plus c, that constant integration at the end. So when we integrate x times the sine x dx, our answer is going to be negative x cosine x plus the sine x function plus a constant. So here's our first example. I'm going to leave space here. We'll come back to it because there's a shortcut that you're going to enjoy. All right, but before we do the shortcut, let's do example 2 and example 3, okay? So let me flip over our board, okay? Now let's take a look at example 2 and example 3, okay? So example 2, now your formulas are on the other side, so you'll have to refer back to them. We'll talk about it. So example 2, let's go ahead and integrate x squared times the natural log x times dx, all right? So again, first consideration, you have to think to see if any of your Calculus 1 techniques are going to work for you here, okay? Can we use U substitution? Is there anything from Calculus 1 that works? And so you exhaust all those possibilities. No, Calculus 1 techniques aren't going to work here. So now, what is our new consideration today? Well, integration by parts could possibly be integration by parts. Let's look at the integrand. You do have the product of two functions. We know integration by parts comes from the product rule. So integration by parts, it is our consideration. This is the method we need here. So we're going to integrate by using integration by parts. First thing you need to do is we need to know what the u piece is, okay? And then we need to know what dv is. We need to break the integrand up into u and into dv. U and dv, all right? Now, how do we know which which piece to be u and which to be dv? All right, remember that those letters L-I-A-T-E. L-I-A-T-E. I latent, the I is after the L, or whatever you want to do with that. L-I-A-T-E, logarithm, inverse trig, algebraic, trig, exponential. Okay, what do we have here? X squared is algebraic. X squared is an algebraic function. Anytime the variable is in the base and your constant is in the exponent, variables in the base is algebraic, okay? And then what do we have here? Natural log of x, well, that's a logarithm. That's a logarithm, all right? So we have a logarithmic function, we have an algebraic function, L-I-A-T-E. As you go through those letters in that order, what comes first? L, the logarithm. U is going to be your logarithmic function. U is going to be natural log x. Okay, what about dv? dv will be the rest of the integrand. So d is going to be x squared, dx, it's the rest of the integrand. Okay, all right. Then what do we need to do? We need the rest of the pieces for our formula, remember? So we have u is the natural log x. We need to know what the differential of u is. We need du. So du, when you find the derivative of natural log x, remember this from Calculus 1? Natural log x, it's 1 over x dx. There's your derivative formula, okay? Now, what about, then we need v. We need v. We know what dv is. How do you go from dv to v? You would integrate, okay? So to get from dv, the derivative, to the function, you integrate. Integrate x squared, and we're at x cubed over 3. All right, so here are the pieces. Once we've made a list of our pieces, let's go ahead and write it out, okay? So our integral of x squared, natural log x dx, okay? So we're gonna have u times v. So we're gonna have natural log x, okay? That's gonna be multiplied by x cubed over 3. U times v, all right? Subtract from that the integral of v, which is x cubed over 3, okay, times du, which is 1 over x dx. All right, so we're here. All right, so here is just setting it up. So the integral of u times u dv is going to be u times v minus the integral of v du. All right, let's go ahead and simplify here. All right, so our integral x squared natural log x dx, all right, is going to be, let's call this x cubed natural log x over 3. We'll kind of condense the first term to look like this, okay, minus, I'll pull out the 1/3, all right, and then one of these x's cancels, so we're just going to integrate x squared, okay, so just simplifying our answer a little bit here, all right. Now let's do this integration and write our final answer. So the integral of x squared natural log x dx, okay, our Our first term is x cubed natural log x over 3, okay, minus, and then you have 1/3 here being multiplied by integrate x squared, and you get x cubed over 3, all right? And then finally, we're done with the integration, but don't forget to put the plus the constant of integration, okay? So this is, I'll leave the answer here. You can change this and write it x cubed over 9 if you want to simplify, or you can leave it here. All right, so however you want to represent your final answer. So here it is, okay? Integration by parts. Okay, so integration by parts, and here we are. All right? Okay, so here's example 2. All right, and then finally example 3. Let's take a look at this example. So we want to integrate x squared times e to the 2x dx. Okay, so we want to integrate this. All right, first consideration, are there any techniques from Calculus 1 class, use substitution, that may work here? No, they're not going to work. And you can try that, fiddle around with that on your own. So the Calc 1 techniques won't work. So Calc 2 techniques, all right? Well, you know, integration by parts, you do have the product of two different functions. We have the algebraic times the exponential, so, and we know integration by parts comes from the product rule. So, you know, you take that as a hint. If you see that you have the product of functions in the integrand and your Calculus 1 techniques aren't working, integration by parts will be your consideration. So we want to take this integrand, we want to break up the u piece, okay, and we want dv. Okay, so I'll write it over here so I'm not space, okay? So u and dv, well, what do we have here, okay? So when we make our consideration, the li, a, t, e, right? So li, a, and t, and e, all right? So what kind of functions do I have here, all right? X squared is an algebraic function. X squared is algebraic. And then e to the 2x, this is exponential, okay? Algebraic and exponential, all right? Anytime the variable is in the base, it's algebra, right? Anytime the variable is in the exponent, it's exponential, all right? So that's, we have an algebraic and exponential. As you go through the LIATE, going down that list, which function comes first? The algebraic. X squared comes first. U will be x squared, okay? So dv, all right, so what about dv? It's the rest of the integrand, e to the 2x dx. So that's the rest of the integrand, all right? Then what do we need? The rest of the pieces, okay? We need the rest of the pieces. We know what u is, we need the differential du, okay? So du, we're gonna take the derivative of x squared, 2x, multiplied by dx. There's our differential, all right? Now, dv is e to the 2x. We need to know what v is. So how do you go from differential to function? We're going to integrate e to the 2x, okay? So use substitution here, so u would be the exponent 2x, going to require you to pull out a constant up front. When you do integrate e to the 2x, you're going to have 1/2 e to the 2x, okay? So we're here, all right? So now let's go ahead, and so we're going to integrate x squared, e to the 2x dx. Do this integration. All right, remember the formula now, it's on the other side of the board. It's u times v. U times v is, you're going to have x squared times v is 1/2 e to the 2x, okay, minus the integral of v, which is 1/2 e to the 2x, all right, and then du, which is 2x dx, all right. So we have this, all right? I'm just going to rewrite this line to simplify our pieces, okay? So we integrate x squared e to the 2x dx, all right? So we see that we have u times v minus the integral of v du. Let me just simplify. So let's take this term right here, and we can call it x squared e to the 2x over 2, all right? Minus, okay, and these twos, a half of 2, these cancel, don't they? Okay, so 2 goes into 2 once. These constants, they cancel here, okay? So I'm just going to integrate x e to the 2x dx, and so we have this, all right? Okay, so now how do we integrate this? Okay, so how are we going to integrate the integral of x e to the 2x dx, okay? What we have to do here is we're going to have to use integration by parts again. Okay, so we have to use integration by parts twice in this one problem. We have to use integration by parts again. Okay, all right, so just here, let's go ahead and take a look. All right, so I need my u piece and I need my dv piece for this term right here. Okay, now again, I have an algebraic and an exponential, so u is going to be the algebra, and then dv is going to be the rest of the integrand, e to the 2x dx. It's going to be all the rest of the integrand. I need my differential here, so du will be dx, okay? And then I need to integrate e to the 2x. When I integrate, don't forget to pull out the constant 1/2 e to the 2x is what I end up with here, okay? Just as we did above, all right? So integration by parts again, so we have x squared e to the 2x dx, all right? So that is going to equal, we have our first term here, x squared e to the 2x over 2, that's not going anywhere, okay? Minus, now grouping symbols, okay? Be careful with grouping symbols because you're going to have to do, integration by parts generates the two terms, and this negative sign, this subtraction needs to be distributed to each of the two terms, okay? So here we go, u times v, that's going to give us x e to the 2x over 2. U times v minus the integral of v, which is 1/2 e to the 2x, okay, times du, which is just dx. Okay, so running a little bit out of space here, but that's what we have now. All right, and then let's go ahead and simplify. So the integral of x squared e to the 2x dx, okay, is going to equal x squared e to the 2x over 2, that's our first term, okay, minus, distribute the negative sign, minus x e to the 2x over 2, okay, and then minus a negative, so be careful with distributing the sign minus and negative, that's going to be a positive. We need to integrate this though, okay, so when you integrate 1/2 times e to the 2x, and you integrate that, you're going to have 1/2 times 1/2 e to the 2x. It's going to generate another 1/2, so you're going to end up with e to the 2x, right, over 4 when you integrate this term, okay? And then indefinite integrals are never complete until you add on that constant of integration. Don't forget plus c. So example number 3, integration by parts twice. Integration by parts twice here, and these are the terms you generate when you work through this example. So this is integration by parts. All right, we're going to go back to example number 1, and let's take a look at how the shortcut will work. Okay, so let's go back to example number 1 and let's take a look at the shortcut. The shortcut is called the tabular method. Okay, there's a shortcut for doing these. It's a tabular method, so if you're allowed to use them in class. So we're going to set up a table. All right, so we're going to set up a table with 3 columns. The first column is going to be SIGN. Okay, so the first column is SIGN. Okay, for positives and negatives. Second column is going to be your U column. Third column is your DV column. Okay, so we're going to set up a table here. All right, and that's, we're going to set up a table. Your SIGN column, not to mix it up with the trig function, that's why I'm spelling it. Your SIGN column, which is always just start positive and alternate signs. Okay, positive, negative, positive. All right. Your U column, let's take a look, because this is when we integrated x times a sine x. What did we use for U? We used x for U, so put the x in there. Okay. Now your U column, what did we do with the U? What we did with the U is we needed to find its differential. So you're going to go down the column, you're going to differentiate whatever you put in the U column, find the differentials, okay? But you're not going to put the differential notation, just find the derivative. So what is the derivative of x? It's 1, and then again, what is the derivative of 1? Derivative of a constant is 0. All right, and then what about the dv column? What did we let dv equal? We let dv equal the sine of x. Okay, now what did we do with our dv? We had to integrate to get v. So as you go down your dv column, you're going to want to integrate the terms. Integrate sine x. When you integrate sine x, you get negative cosine x. Okay, and then integrate negative cosine x. When you integrate the negative of cosine x, you get negative sine x. Okay, because you're going to bring the negative with you. Okay, so this is how you set up your table. Okay, SIGN starts positive, alternate, and then you have your U and DV, the pieces that you need in the formula, okay, in the integrand. U and DV, LIATE to figure out which piece. U piece, differentiate, okay? DV piece, integrate. Now here's how you read the answers, okay? So you're going to start here where the positive sign is, okay? So you're going to start here, you're going to go across, right? And then diagonal. That makes up your first term. That is, so positive x times negative cosine x is your first term. All right, and then minus, so you're going to go cross, diagonal, there's your second term. Okay, all right, go across. Okay, well then you're multiplying something by 0. So once you hit the 0, you're done. Okay, so now, so let's write down what we have here. So the integral of x sine x, so the integral of x sine x dx. And we're just going to read it off the table. We have positive x times negative cosine x. Well, that's negative x cosine x. That's our first term, okay? Let's read the next term. Negative times 1 times negative sine x. Well, your negative times negative is going to be positive, okay? And sine x. All right, and then once you hit the 0, no more terms to list here. And then don't forget it's an indefinite integral. So as always, we need that constant of integration. And here is your shortcut. Isn't this an incredible shortcut? Okay, comes in handy, especially if you're having to perform an integration by parts and you have, you know, a time constraint on your test, quiz, whatever you're taking. Okay, so that tabular method is your shortcut. All right. Now, for me, the shortcut doesn't work for all, you know, really the shortcut, let's take a look with example 2, okay? Because for me, the example 2, the shortcut's not going to work very well for example 2. All right. So, let's get this in here. So the shortcut is, so remember how the shortcut works, right? Okay, so the shortcut, your first column is SIGN. Your second column is U, and your third column is DV, okay? So this is how you're going to set up your table, all right? Your SIGN column always starts positive, and then you're going to alternate signs, and you keep going through here. Your U column, okay, what did we let U equal for this problem? Natural log x. What you want to do with your U column as you go down is you want to differentiate. When you find the derivative of natural log x, the derivative of ln x is 1 over x, okay? Then you want to differentiate again. The derivative of 1 over x is negative 1 over x squared, okay? Now what's happening here is when you use the tabular method, I like to have the derivative converge onto 0. And as you find the derivatives of your u's, this is never going to get to 0, okay? So for me, you know, you might have other shortcuts out there, but for me, tabular method's not going to work for example 2, right? Tabular method works beautifully when u is an algebraic, when u is the algebraic whose derivative converges to 0. Then it's going to work beautifully, okay? So that's for this problem here. Right, and now how about example 3? Will the table method work well for example 3? Right, so I'm going to need to give myself a little more space on the board here so I can show you the table method. I'm going to erase some of this example number 2. All right, so let me move some of this example number 2 out of the way so I can show you the table method for example 3. So example number 3, tabular method. All right, so let's take a look at this. So here's example 3, tabular method. right, we'll call it shortcut for more fun. Okay, so what about example number 3? Look at all this work we did over here with example number 3. Okay, well, so let's take a look at SIGN and then U and DV. Okay, so let's take a look at the tabular method for example 3. All right, SIGN, start positive and alternate signs. Okay, so positive, then negative, positive, you're going to alternate signs. Okay, our U column is x squared. Okay, so we're going to put x squared in our U column. That's where we started. And what do we want to do with our U column? We want to differentiate. Derivative of x squared is 2x. Okay, we want to find the derivative of 2x is 2, and then derivative of a constant is 0. Okay, so you see, it does converge to 0. This is going to work very beautifully. dv column, dv is e to the 2x. So e to the 2x, that's what our dv is, okay? What do we do with dv? Where did we go from dv? We went from dv to v. We want to integrate as you go down the dv column. When you integrate e to the 2x, you're going to get 1/2 e to the 2x, okay? Use substitution involved in that. Integrate 1/2 e to the 2x, you're going to have 1/4 e to the 2x. Integrate 1/4 e to the 2x, it's going to be 1/8 e to the 2x, okay? Because you needed to continually pull out a 1/2, okay? And then how do we read our answer? Start in the upper left, hit the plus sign, and you're going to go across, diagonal. That's your first term, okay? You're going to go across, diagonal. That's your second term. Across, diagonal. That's your third term. Keep going until, because you're multiplying the terms. When you multiply by 0, it goes away, okay? So what do we have here? We wanted to integrate x squared e to the 2x dx. We want to integrate this, okay? So what do we have using the shortcut table method? Well, positive, you have x squared times 1/2. So you're going to go across and diagonal and multiply these, okay? So that's where you get x squared e to the 2x over 2. There's your first term, okay? Then your next term, you got the subtraction sign here, so subtract, and now we have 2x times 1/4 e to the 2x. So 2 over 4, that's 1/2, isn't it? So that's going to give you x e to the 2x over 2, okay? The 2 over 4 cancels, so you have x e to the 2x over, 2 over 4, so over 2, okay? And then plus, okay, plus a positive term here. 1/8 times 2, so you have 2 over 8 e to the 2x, and 2 over 8 is 1 over 4, okay? So it's e to the 2x over 4. So e to the 2x over 4, okay? And then your fourth column is where the 0 is, so here we are, but don't forget to add on your constant of integration. Anytime you're dealing with an indefinite integral, after doing all this work, don't forget that constant of integration, okay? So the great news, this tabular shortcut method works beautifully. Look at all the work we did here. Make a table, works beautifully, okay? All right, the disadvantage of the tabular method is, for me, it doesn't work on the types of functions that have u as a logarithm. So it doesn't work every single time, but works beautifully when u is an algebraic whose derivative converges onto, goes to 0, okay? So I hope this helps you get started with integration by parts. I'll come back and do more videos. Thank you for tuning in and staying tuned in. I hope you did that. So good luck with your endeavors, and I will see you in the next video. Thank you.